is chapter, well, line integrals I actually started to do on Friday, but what comes first is the notion of a vector field or force field, and that's what I'm going to do today. And then tomorrow I'm going to do the line integrals. So this is chapter 15.1. Okay, this is 15.1, vector fields. Okay. And tomorrow what I'll do, I'll continue what I was doing the other day with a line integral, and then we're going to put the vector field together with the line integral to find the work done in a vector field or force field. We'll put those two together. But let's talk about the vector fields. The book does this first, and WebAssign does it first. What is a vector field? A vector field, okay, what it does is assigns a vector to each point in the plane. Okay, so each point is given a vector. Let's say 2x, 2y, for example. This would be an example of a vector field. And generally, the way to draw these vector fields is to take all the vectors that have the same magnitude and draw them together. For example, the magnitude of each vector in this field would be the x component squared plus the y component squared. Take out a 4 as a 2. The magnitude of each vector would be 2 times the quantity x squared plus y squared. And what you want to do is then plot those vectors that have magnitude 0, and then those that have magnitude 1, and then those that have magnitude 2, and see what you get. Okay, and that's what you would do. Let's take all the vectors in this field where the magnitude is 0. So what do we get? We get 2 times the square root of x squared plus y squared equals 0. What points make that equal to 0? If you square both sides, divide by 2 first, square both sides, you get x squared plus y squared is 0, and that's 1.00. It's at that point this vector field has vectors that are of length 0. Not that interesting. Let's do the ones where the magnitude is equal to 1. So, yeah, 1. Square both sides. Divide by 4. So all the points in the plane where x squared plus y squared equals 1/4, at those points, this vector field has vectors of length 1. So let's see. What are we describing here? What's x squared plus y squared equals 1/4? It's a circle whose radius is 1/2. So all the points around this circle have the same length 1 vector. So let's plot a couple of them. Okay? For example, this is x squared plus y squared equals 1/4. This point would be 1/2, 0. What vector are we looking at? At 1/2, 0, the vector is 1, 0. It's this vector. Okay? Let's take another vector in this around this circle. Let's take, let's say we could take, let's take 0, 1/2. That's another vector here. 0, 1/2 would be this vector. Then you would have this vector. And then you would have this vector. And actually what would happen is at this point you'd have this vector. All these vectors have length 1. Okay? All those vectors have length 1. And then you say, okay, let's take a look at all the vectors in this field whose length is 2. Okay? So, the magnitude, which is 2, square root of x squared plus y squared equals 2. Divide by 2. Square both sides. Okay. Every vector around this circle, x squared plus y squared equals 1, These vectors are 1. So that's, they would be in here. All those vectors would have length 2. So at this point, you'd have this vector. 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 This vector. Like so.
Is it always normal to?
No, they're not necessarily normal. So many times they are not. In this particular case, they are. That's a good question, because sometimes they are not. Okay, it's not the same thing as the level curves and those vectors perpendicular to the level curve. These are those vectors having that same length. For this particular vector field, they are normal to that circle.
How do you know they're like that then?
Oh yeah, I just kind of know. If you were to take this point here, let's take 1 over the square root of 2, 1 over the square root of 2. That would be a vector that would be a point that satisfies this. That is to say, at this point, that's a point on this circle, okay? Because that'd be 1/2 plus 1/2. And then you substitute it in here, you get 2 over the square root of 2, 2 over the square root of 2. That would be this vector, and its length is 2. And it's true for all of them. But that is not necessarily true. That's a coincidence in this particular case. Okay? So you can get an idea of what this vector field looks like by looking at these vectors that have equal magnitude. Okay? And that's generally how these are drawn. Teddy?
No, I totally forgot. Sorry.
Oh, that's okay.
I had a real question though.
I'm sure you did, man. All right, that's okay.
How would your dimensional ones where vectors go in 3 spaces?
3 space. We got 3-dimensional vector spaces as well, and you do those the same way. Now, those are a little bit more difficult to draw, and we're not going to actually draw them, but you would do them the same way. You could do them the same way. Brandon?
Wait, was the question like they're all normal to the circle?
Yes.
So how would you make it so it's not? Like, what would be the point?
If you had something like this, okay. Everybody else up with this one? Yeah, go ahead, Dave.
So are those circles sort of imaginary? Or
Yes, they are.
So you
They are. They're not part of the field.
They would just come out of whatever points that is.
Yeah. What I'm saying is that every point on this circle has a vector that has length 2. Now, the fact that it turned out to be a circle, I mean, it could be anything else. If we take another field, we may not get circles at all. Yes?
Question. How did you get that 2 out of the magnitude? The 4x squared plus 4y squared up on top?
Yeah,
How
there.
do you get the 2 out?
Here's what you do.
Sorry.
There. You don't have to apologize ever for asking a question. Okay? You factor out a 4, okay? And then you take the square root of 4 out as a 2. You don't ever have to apologize for a question, ever. Okay. And in 3-space, vector space, you would do them the same way, except they're more difficult to imagine and to do. Then you would let Mathematica do it. Mathematica will do vector fields. Liam?
When you're solving for the magnitude, that base of the magnitude is going to create its own function, and that's going to be the pattern in which these.
Yeah, exactly. That's exactly right. Let's do another one. Let's take another vector field. Let's take this field. Oh, let's take the field. Let's take a very simple field. 1, 1. That's too simple. Okay, but let's do it. This is a stupid field. Okay, this is a stupid field. Here we go.
Everything is along a linear line.
Yeah, 1, 1. Here's a vector field, but it's assigning a vector 1, 1 to every point. Now, if you do what I just said, let's take a look at all the vectors have length 0. Well, there aren't any. Okay, how about all the vectors have length 1? Well, there aren't any. All the vectors in this field have length square root of 2. Okay, so they're all the same. So here's one where, here's your field. Every point has the vector 1, 1. Okay? So this would be this vector field.
It's like that scene 300 with a fight Robbie there.
Yeah. Yeah, I've got a funny story about that movie, though.
You were there?
I am part Greek, though. I am part Greek. I don't know, but it's more on the eastern part, near Turkey. But anyhow, no. It's just that I was at the gym. I had my iPod. This was several years ago. I was on the bike, and I had the movie on my iPod. 300. I just to do the bike and watch the movie on my iPod. The movie had just come out. What's that?
I said I usually watch Rocky when I'm working out.
Oh, that would be appropriate. That's true. I had the movie on there. I hadn't seen the movie, and just so I can amuse myself on the bike. So I'm on the bike, and this woman was right next to me on her bike, and I'm on my bike, and I'm watching the movie. And then, right at the beginning of the movie, he and his wife,
there's a scene in the room.
and there's a scene there where he's with his wife. And I could see her looking over at the iPod, thinking, "Here's this guy in the gym looking at porn when doing it." I was so embarrassed. I took my iPod. I don't know what I did. I just shut it off.
Yeah, you made it look way worse. Dude.
Was that
Suck it out.
I know, but that was the movie 300. That was it, right in the beginning. All right, but anyhow.
Should have gone with Rocky.
You're right. Anyhow, so here's a field where you just get every vector the same length. They're all at 45-degree angles. Liam.
So the vector itself is just one arrow.
Yes,
One
at a single point. Every point has its own arrow.
But this vector is only defined at one point of x and one point of y. So then how is there a field of multiple?
Every point xy in this plane has a vector 1, 1 attached to it. That's what this field does.
Okay.
So this vector field is a set of an infinite number of vectors. Every point has the same vector 1, 1.
So you're saying a vector field defined by this vector.
Oh, so
I'm saying here's the vector field right here, and this is assigning the vector 1, 1 to every point.
it's almost like a unit vector from every single point or something. I don't know.
It's like that, but it's this
Like
vector
so
here.
they're everywhere.
I'm going to do one in between the two. Go ahead.
How did you get that equation on the last one, like the square root of 4x squared? What is that?
The magnitude of a vector here. Generally speaking, what you do. No, that's okay. They're represented by m and n for some reason. I don't know why. M and n are functions of x and y. The magnitude of the field and then what you do is you let it equal some constant. It's like finding level curves, right? Where you then change the constant, which is somewhat of an oxymoron. You're changing the constant from 0 to 1 to 2 to 3, and you're finding all the vectors that have the same magnitude and graphing those guys together. Let's do one more. Let's do another one. Let's do one in between the two. Let's suppose we have the vector x1. Okay. What does this field look like? Well, let's find the magnitude, and let's set the magnitude equal to a constant and see if we'll draw all those vectors of equal magnitude. So, magnitude. Okay. Set it equal to some constant c. Okay. Square both sides. Okay. So, here, and we can square both sides. I can let c equal, let the constant, let's see, okay, let c equal 0. Start there. What vectors have a magnitude of 0? Well, those vectors where the square root of x squared plus 1 is equal to 0. If you then square both sides, x squared plus 1 equals 0. X squared equals negative 1. Well, there aren't any vectors of length 0. Okay, that's what that tells you. Let's take c equal 1. Let's take all the vectors that have length 1. Well, here's the magnitude, square root of x squared plus 1. set that equal to 1, square both sides. So x squared equals 0, and x equals 0. So we want all those vectors that have length 1. Those vectors are the vectors whose x-coordinate is 0. Okay? That would be the vectors along the y-axis. So let's take 0, 0, for example. When x is 0 and y is 0, we get the vector 0, 1. When x is 2, let's jump to, let's go to 1. When x is 1, x has to be 0. As long as x is 0, 0, 1 is our vector field, okay? So that's the one vector that has length 1. It's that one vector, and that's it. What about all the vectors of length 2? This is really a stupid field. Let's square both sides. Okay, this is something else. Now we got somewhere. So x squared equals 3. So x is plus or minus the square root of 3. So the vectors whose length is 2 are those vectors where x is plus or minus the square root of 3. So square root of 3, 1. Jesus, this vector, square root of 3, 1. That's this point, and its vector is square root of 3, 1. Wow. I'm glad I took this field here, all right? When x is the square root of 3, okay, anytime x is the square root of 3, okay, for all the vectors here where x is the square root of 3, all those vectors on this line have length 2. Okay, so.
Where are they pointing specifically?
Okay, so here's x is the square root of 3. I'm saying that every point on this, here, let's take this point. Square root of 3, negative 3, say. Okay, here's a point. What is the vector at this point? The vector at this point is the square root of 3, 1. Square root of 3, 1. Let's take this point. When x is the square root of 3 and y is 0. What's the vector here assigned to this point? It's the square root of 3, 1.
So C is the
Length of each of these vectors.
of the length.
Yes. Every vector along on this line has length 2. Okay. Not only that line, but on this line as well. Okay. When x is the negative square root of 3. So there's a point. Negative square root of 3, negative 3. What vector is assigned to this point? The vector is negative square root of 3, 1. That would be this vector.
So,
Go ahead.
how did you choose the points on the line exactly? Like,
I'm as long as I give them an x
so it can
coordinate,
be any point on the
and
line.
any point, any y coordinate on that line. What I'm saying is,
All right.
by setting the magnitude equal to 2, okay, what must be true? Well, x has got to be plus or minus the square root of 3. So for every point along this line where x is the square root of 3, no matter what the y is, it doesn't matter. It's being assigned the vector x1. What's this vector x1 at this point? Well, it's the square root of 3, 1. So go over the square root of 3 and up 1. Go over the square root of 3 and up 1. Go over the square root of 3 and up 1. That's what it's doing. What happens over here when x is negative square root of 3? It's assigning the vector negative square root of 3, 1. That's this vector. What about, let's take another point. Let's take this point.
Wait, so is this
Okay.
square root of 3 away from the y-axis?
The negative square root of 3 is any point on this line. And I'm saying, okay, let's take one point on this line.
No, I'm just saying that's square root of 3 on the on the x-axis. That's what it is. Negative square root of 3. That whole line going down.
Okay, this line?
Yeah.
Yeah. Okay.
This line here is x equals square root of 3.
Yeah, that's what I'm asking.
Yeah. And this line, x is negative square root of 3. And let's take another point on this line. Let's take this point, which is negative square root of 3, 0. What is this vector field assigning to this point? What vector? Well, negative square root of 3, 1 is the vector assigned to this point. Now, negative square root of 3, 1 is this vector. And what's the length of that vector? 2. Every point on this line has a vector of length 2. Every point on this line has a length 2. All the points in this one and this one. This vector field, now let me go back to 0, 0 again. Okay? At 0, 0, this point, the vector assigned is 0, 1, this vector here like I have. Okay. I hesitate to do this, but what's going to happen when I take the vectors along these two lines, where the c is equal to 3? Those vectors are going to look like this and have length 3. Okay? That's what those are going to be. And over here, you're going to have these vectors.
What would they be at the plus or minus like square root of 8 or something?
Yeah, yeah. Well, let's do it. Let's say c is equal to 3 now. So what do we have? Square root of x squared plus 1 equals 3. Square both, just exactly what you said. Square both sides, x squared plus 1 equals 9. X squared equals 8. So x is equal to plus or minus the square root of 8. That's what this line is. X equals the square root of 8. This is x equals a negative square root of 8. Every point on these lines has a vector whose length is 3. The vectors on this line look like this. Because what do they look like? They look like square root of 8, 2 square root of 2, 1. Okay? So square root of 8, 1, square root of 8, 1, square root of 8, 1. And please note, all of these have length 3. And the same with these have length 3. That's what that field looks like. Whew.
And that's all based off of like what you choose for your C values.
Yes, yes. You choose a C, C4, C equals 5, C equals 6, etc. One thing about the C values here that's different from the level curve C values, these cannot be negative. The magnitudes of these things cannot be negative. So you have to have C starting at 0, 1, 2, 3, etc. Now, have we ever dealt with vector fields before? Have we had a vector field before? We did. Well, and that and that vector field was what? The what? No, the gradient.
It was this guy.
Yeah, I think it was. The gradient. Now check this out. We started with a function. Here's our paraboloid. Okay. The gradient is what? A vector in the xy plane that points in the direction of maximum change. In other words, what does the gradient do for this function? It assigns a vector to each point in the xy plane that's pointing in the direction of maximum change. This gradient is a vector field. Now, because this vector field was generated by being a gradient to a function, it's a special vector field. Okay? This vector field is said to be conservative. Okay? It's conservative. Okay? Because there's some function that has it as its gradient. Now, is that going to be true for all vector fields? And the answer is no. Not all vector fields are gradients. The conservative ones are. Okay? The function itself is called its, do you guys know this stuff? Conservative vector fields and potential function or potential. Okay? This is a conservative vector field because it has a potential function, a function for which it is its gradient. Okay? You with me? Okay. Let's take, let's take the last one I did. I did x1 here. Okay? Let's take this vector field. Now, question is this a conservative vector field? Is it possible that this is the gradient for some function, its potential function? And the answer is no. It's impossible. You can't come up with a function that has this as its gradient. Okay? This is non-conservative. Now, how do we tell? Is there a test? Yes. There's a test to see if a vector field is conservative or not. So here's the test. It's conservative if the partial of n with respect to x, it's kind of somewhat counterintuitive, you got to take the second one with respect to x, is equal to the partial of m with respect to y. Okay? If that's the case, the field's conservative and it has a potential function, okay, that we are going to be very much interested in. So, let's test it. Let's test first this field, which we know is conservative because we know it's the vector field for this potential function, but let's test it out. Here's m, here's n. Partial of n with respect to x is equal to, what's the partial of n with respect to x? It is 0. And the partial of m with respect to y is also 0. That means this is a conservative vector field. That means it has a potential function. Okay? In other words, this is the gradient for some function. Can we find out what the function is? Can we, what's called, capture the potential? Liam?
So, I mean, a gradient is a partial derivative of a function.
It's a vector that gives you, who's formed by the partial derivative with respect to x, the partial derivative with respect to y. Yes?
So wouldn't it be possible for it to be a gradient if you could just integrate the x and y?
That's what we're going to do. That's what we're going to do. But see, the thing is,
x1, couldn't you?
no. See, let me do it for this one, then we'll try to do it for this one. Okay? Here's the deal. Okay, we know this is conservative. We know it has a potential function. There's some function for which this is its gradient. If that's true, okay, the function's partial derivative of that function, the one we're looking for, with respect to x, it must be equal to 2x. Okay? In other words, how do you make the gradient? It's what Liam just said. You make the gradient by taking the partial with respect to x, and the partial of the function with respect to y must be equal to 2y. That's how you make a gradient. Okay? Take the partial with respect to x, that's the x component. Take the partial with respect to y. So what's our function? What we're going to do is integrate the 2x with respect to x. Okay? What's the integral of 2x with respect to x? It's x squared, okay, plus a constant in terms of y, possibly. Because in this context, y is a constant. The constant of integration here could be a function of y. Also, our function, when we integrate this 2y with respect to y, what's the integral of 2y with respect to y? It's y squared, plus possibly a function with respect to x.
So in order for that to work, they both need to be the same.
In order for this to work, we have to what's called reconcile the two, come up with a function that meets both requirements, and that function is x squared plus y squared. Because that function is x squared plus a constant with respect to y, And this function also is y squared plus a constant with respect to x. This is its potential function, and how do we know? Take the partial with respect to x, you get 2x. Take the partial with respect to y, you get 2y. Done. Let's try to do the same thing with this function. Now, is everybody okay with this one? Okay, no problem. Adrian, how you doing?
Good.
Okay. Okay? Let's see what we got here. So, here's our vector field. Let's test for conservative. Partial of n with respect to x is, n with respect to x is 0. M with respect to y is, it's also 0. It is conservative. What a jerk. So this one is conservative. We can capture its potential. 1x is not conservative. I'm going to do that next. But let's get its potential here. So here's what we have. The partial of this function is x. So integrate with respect to x to get x squared over 2.
Is this a differential equation?
Yeah, it is a differential equation, really. And you're solving it by separating variables and integrating both sides. That's the first thing you learn in diffie-qs, right? Separate the variables and integrate each side. Partial with respect to, of course, you're not using partials at that time, but still, it's the same idea. Partial with respect to y is 1, so our function is the integral of 1 dy, which is y plus a constant. So, what's our potential function here? X squared over 2 plus y. Okay, so that does work. And when Liam said, yeah, you could capture that potential just by integrating, he was absolutely right. But let's take a different example. Let's take this example. Let's test for conservative. Partial of n with respect to x, 1. Partial of m with respect to y, 0. These are different. This is non-conservative. Go ahead, Lee.
Would you have a vector where the x would be in the second?
Sure. Each of these can be functions of x and y. Yes. So here we go. Our partial, here's what we're going to do. We know it's non-conservative. There can't be a potential function, but we're going to try to find it anyways. Okay? And we'll see what happens. Okay? Partial of our function with respect to x has to equal 1. That means our function is the integral of 1 dx, which is x plus some constant, a function of y. Okay? That would have to be true if it had a potential function. Also, the partial of the function with respect to y would have to equal x. Therefore, our function would be equal to the integral of x dy, which is xy plus a constant with respect to x. You cannot reconcile the two. You cannot come up with a single function of x and y that meets both requirements. There is no function. And you may say, well, what about x plus xy? Well, it doesn't really work. X plus xy is okay for this guy, but it's not okay for this one. Okay? You can't come up with one. It can't be done. Okay? This is a non-conservative vector field. And that's going to make a huge difference when we find work done in that non-conservative vector field. Because what's going to happen is this. We're going to be finding work in a vector field. Now, if it's a conservative vector field, and if we start here and do some path and end up at the beginning, the work done in that conservative vector field is going to be what? 0. That's 0 work. But in a non-conservative vector field, it's conceivable that you get back to the beginning and the work done is not 0. It could be something other than 0 in a non-conservative vector field. Okay? Gravitational field is a vector field in 3 space. Yeah, we haven't talked about 3 space yet. Is gravitational field a conservative vector field?
Yes.
Yes, it is. It is conservative. If you're going to move something from here to here, it doesn't matter what path you take. Okay? Any path you take, you're going to get the same amount of work done. Even if you go up here, over here, down here, and over to here again, the amount of work done is the same as the amount of work going from a linear straight line path or a curved path or any path from here to here. The work done is the same in that conservative vector field. In a non-conservative vector field, it may not be the same. Okay? So that's what we're going to be looking to do. We have to do. Yeah, we can do a field in 3 space. Let's do it. All right. Here's what we got. So here's the deal. You got a vector field. You draw it by finding all the vectors of the same length. Okay, and plotting that. That's not all that critical. You test to see if it's conservative in a vector field in 2 space. Taking the partial of n with respect to x, partial of n with respect to y, and see if they're equal. If they are equal, it's conservative, and you can get its potential function by doing those integrals. If it's non-conservative, there is no potential function. Okay? Let's go to 3 space. A little bit more difficult. To do 3 space, we have to define what's called the curl of a vector field. You guys do this at all? No? No.
Is this going to fit on a quarter of a page? 'Cause that's all.
Oh, no. This is not going to. Oh, man.
5 minutes.
Wow. 5 minutes and, yeah.
That's a good question.
What's that?
Really good chapters test.
Tuesday. A week from Tuesday. Your final is whenever it's scheduled. I don't know. The last day of classes is Wednesday, the 16th. I'm going to give you a roadmap for the final. But the test for this stuff is Tuesday. Believe it or not, it sounds like there's a lot. This is going to be pretty simple.
Tuesday was the last day of class.
Wednesday, the 16th.
Yeah, we go forever.
Nah, it's not forever.
It's
It ends, Teddy.
unpredictable.
The nightmare will end at some point.
Wait, when do finals be?
The final is on the 17th. Yeah, that's what it is.
Literally go up to Christmas.
Almost. The last final is the 22nd, I think.
Yeah, Tokyo will probably give us a homework due on.
All right, let me do 3 space.
Kind of fit this last section in.
All right. Given. Let's say we're given a vector field, in 3 space. Now, m, n, and p are functions of x, y, and z. Okay? And what this vector field is doing in 3 space, it's assigning a vector to every point in space. Okay? First of all, we've got to find the curl. The curl of this function is equal to the curl is equal to I, J, K, partial with respect to x, partial with respect to y, partial with respect to z, m, n, p. Often, this is done by taking del dot f, okay, cross f rather, del cross f. Right? Del is the gradient. The gradient is what? The partial derivatives. F is MNP. Okay? When you take their cross, this is how you take their cross product, right? IJK, take the partials, and then take the function itself. And you may argue that this is just merely a mnemonic device and not really a true 3x3 determinant, and you're correct. At this point, these guys are called differential operators. That's what they're called. And let's do an example of one, okay? Let's do an example of one. Let's suppose we have, and I got to do one more thing here, the definition. The vector space in 3 space is conservative if the curl is the 0 vector. curl, this is done in fluids. We don't have fluids here. Do we do a course in fluids? No, we don't do a course in fluids, though.
I think we do. I think
Do we do
started.
fluids?
Isn't that the new one, or am I wrong?
Oh, it could be a new one that is
Dynamics is the new one.
dynamics. There's a, if you take, if you're a mechanical engineer, at some course you take a course of fluids. It's probably a junior, senior level one. What's that?
I think it's optional for some majors, like for I know UMass, so I think so, it's optional.
Oh, really? Okay, could be optional.
Could be wrong.
Well, yeah, I'm not sure either, though. Well, fluids have a tendency to rotate. There are fluids that have a tendency to rotate about a point. It's called rotational, okay? This is conservative. If the curl is identically zero, it means it's irrotational. There's no rotation of the fluid, okay? That's not a big deal. You don't have to know that. If the curl is equal to zero, it's a conservative vector field, and it will have a potential function, okay? The potential function would be a fourth dimensional object, okay? A function of 3 variables. So let's just do one. Go ahead.
So for the two space, the definition was that the partials have to equal each other.
Yes.
Are the partials always going to be zero if they end up equaling each other?
No.
Okay.
No, they don't have to be zero at all. As long as they're equal to each other, need not be zero. Same with this. The partials could be anything at all, but the curl has to be identically zero to be conservative. Let's do one. We'll do, and this will be it. Let's say we have this one.
Is this like a huge proof to show this?
No, this is a huge proof.
Yeah.
This one here right now? No, it's not. It's not. It's not. We can do it. We can do it right now. Oh, but oh man. All right. So here's what we got to do. We got to find the curl. And what's that equal to? It's I, J, K, partial with respect to x, partial with respect to y, partial with respect to z, m, n, p. Okay, you ready? Here we go. Here and here, you end up with the partial of xy with respect to y. I'm crossing this out, minus the partial of xz with respect to z. So what's the partial of this with respect to y? X. And what's the partial of this one with respect to z? X. You get x minus x, which is 0. Okay, here we go. Cross this out, cross this out. We have these two. Partial of xy with respect to x, y. These two. Partial of yz with respect to z, y. Y minus y? 0. Oh. Last one. Cross this out, cross this out. What's that?
Every yes, is it 0?
Yeah. A partial of xz with respect to x, z. Partial of yz with respect to y, z. Z minus z is 0. This is a conservative vector field. Now, let's capture its potential. The potential function. Watch this. We can do this without even... Okay, watch this. Take this integral with respect to x. After all, if this is conservative, we know there's a potential function. Its gradient is this. So its partial with respect to x is yz. But what's the integral of yz with respect to x? xyz. What's the integral of this with respect to y? And what's the integral of this with respect to z? xyz. That's our potential function. Done. Okay, we're going to do more of this tomorrow, and then we'll talk about line integrals and mass of a wire. And then the next day we'll do work, and we're practically done. See you guys. It's good stuff.
Right away before we end up being behind with chapter.
All right, but I got a practical meeting on building 2. I can do it pretty quick here. Oh.